Hello, in this video we're going to talk about the STL, or the standard template library that comes with C++. So you know in Java there's a standard library that has all the normal stuff you're used to, particularly lists and hash maps and a bunch of other stuff. But we have that in C++ as well. There's a lot of things besides the containers like vector and list and all that. But what we're going to focus on right now is those containers. And we're going to focus on the more common ones. So in a typical C++ program that you might find when you are in industry, you're going to use a variety of containers like vectors and lists and sets and hash maps and things like that. So we're going to show how that's used in C++. So far, we've been developing our own, like our own linked list and our own vector class, but obviously that's not very realistic. There's not many scenarios where you need to rebuild these things. Only if you're on some exotic architecture like maybe the older game consoles before you had more standardized ones like Xbox. So all that's kind of going away, and the standard library is more and more powerful. Also, it's a standard template library. Template means the same thing as generic in Java. So generics in Java allow you to use a container, for example, like a set or a list, and put any kind of thing inside of it, integers, strings, whatever. We can do that too, but we call it templates instead of generics. So if we start an example file here, we're going to do things like vector, and then using the same syntax that Java uses, we're going to say, oh, we've got a vector with integers, and we got a vector with strings, and so forth. So that's where the template part comes in. On our website, there are notes about how to make your own template classes. It's also called meta programming. Turns out templates are their own complex language. You can do very powerful things with templates that are kind of way out of hand. You can actually have templates that compute answers, like compute factorial function or whatever in the template code. It's kind of silly, but it's a very powerful language. I don't think Java has anything near the power with templates that we see in C++. But if just a quick rundown, suppose you got a traditional linked list class and it's set up to contain only double values. You can turn this into a template class by replacing all the occurrences of double with a generic placeholder. And then when the user actually goes on to use your linked list, they'd have to indicate what that generic type is. So you would translate it such that before the class definition, you'd say, this is a template class. And you're going to use the label T. You can use anything you want. You could have multiple templates, multiple types in here as well. So with this T, you then replace everything with T. Everything used to be double. And all your functions also have to say that they're parameterized by T. And then when you use it, you just have to indicate what T is going to be this time. What actually happens is when it compiles, it replaces the T with the word double. And if you have another case of this, like a linked list full of ints, you'd have actually two definitions of the class, one for double, one for int, which means, in fact, template classes always have to be fully defined in the header file. You can't separate the definition of linked list functions in a CPP file because you can't precompile the CPP file with stuff like this unless it sees the rest of the class definition. So it's not useful if you're trying to hide your code, you're trying to sell a product, but you want a template class. The template class has to be completely defined in the header file. So if you want to learn about how to do that, it's all explained here. But what we're going to do is use the standard library template functions. We're going to start with vectors. You have to include vector. And here's two examples. I'd have to include string, actually, if I want to use string. Now, to put something in a vector, you can, the notes online on our website say how to start your vector with a bunch of elements already, or to make a certain size of a vector, like reserve space and all that stuff. So you can look at that online. But here's the traditional way to do it. You push back a value. And then vectors support the bracket syntax. They overload that operator. And you have things like size, which of course you don't get with the traditional array. So if we compile this, let's see what's wrong. Oh, yes. So notice I put myvec. Myvec is the one with the integers. So it completely has a problem with this. So it's not very helpful, obviously, but I need to make this myvec too, because the types don't agree otherwise. Recompile this. So pretty straightforward. Now there's also a thing called a list. This is a linked list. It's a doubly linked list, so it has pointers in both directions, so it's just as efficient to go left to right as it is right to left. They have another one called forward list that only points left to right. Obviously, the only time you'd use that versus a list is if you're trying to save space, because you don't want that second pointer for everything. But that's kind of a specialized use case. Let's change this vector to a list, and I'll change the name as well, my list. And you can see we can do my list size. All right, so they each have one thing. Now, why is it called pushback? The STL is full of a variety of container types. And let's look at that list. cppreference.com is always a good site. They have a whole category here called containers. And you see inside here, there's all kinds of containers. So first of all, array is a more recent addition. It's just a little wrapper for an honest array. And it just helps when you want to use the other functions that expect STL containers, but you only really have an array, you can use this class. But otherwise, it really is an array. A vector is like an array, but it allows growing the vector. A deck is a double-ended queue. It is a more efficient structure. It's a more complex structure, but it allows you to put stuff at the beginning and the end efficiently. And then you have your two kinds of lists that I mentioned. So if you click any of these, you see the really important details that distinguish these different containers. So first of all, you see it's standard vector, so it's an std namespace, and it's a template class. And cppreference.com is trying to be as complete as possible, so they have all the details about what that means. But what you have to think about is you have to give a type. There's a second parameter you can give in the brackets that you're not going to use. Now, the elements are contiguous, so they should be pretty efficient to access left to right. When it's contiguous like that, it means you can use the brackets, just like you have an array. Vector is grown automatically. It can also shrink as if it deems it's necessary to shrink or advantageous. They use more space than a regular traditional array. That's because they're holding some positions so that when you add elements, it doesn't always have to grow every single element, right? It'll double in size usually. So those spaces are not used yet. And so it only grows or only contracts with memory is exhausted and so forth. The most important thing that distinguishes these containers are these kind of details. So to access any random element anywhere in the middle, on the right side, whatever, it always takes constant time. So big O1. So if you're taking the algorithms class, this notation means it takes pretty much always the same amount of time, no matter how many things you have. You could have 1,000 things, and it should take just as much time, a few nanoseconds, to get any particular random element or any position. Also, if you're putting stuff at the end, it kind of turns into over time, like average constant time. So it usually takes about the same amount of time to add something to the end, which is a pushback. Amortized constant means there will be some times when it has to grow. And as you know, when you made a vector class, to grow, you have to copy everything from the old to the new. So that's going to take, if there's 1,000 things, you got to copy 1,000 things. But that doesn't happen very often. So it's kind of like it's constant time. However, linear in the distance to the end of the vector. So if you're putting stuff at the end, it takes about constant time. But if you're putting stuff, say, in the front or in the middle, it will have to copy everything. And so if you say there are n things, like you have 1,000 things in your vector, it'll take 1,000 steps. I don't know how long a step takes, a few nanoseconds, but it takes as many steps as you have things. So if you have a bigger vector, it'll take more time to put something in the front of it. It is possible to put something in the front, though. So that function does exist. It's called a push front, I think. And most of these other details are going to be pretty consistent across the other container types. Now compare with a list. So as you know, a linked list is not efficient if you want to get to the middle of it or the far right side or whatever. With a doubly linked list like this one, it might be efficient to go to the right side as well as the left side, but it's not going to be efficient to go in the middle. Since it's not efficient, they don't even let you do it. Because what's the point? Why are you using a linked list if you want random access to elements? So there is no function like the brackets on a linked list. It's pointless to even develop such a function because it'd be so slow. So the functions that exist are insert, which means put something in a particular place if you really have to, but more likely you're going to say push back or push front. So push front is put something on the left side, push back, put something on the right side. Pop and the two versions of pop back, pop front, that mean take it off one of the sides. Now a deck is designed to be efficient for all those kinds of operations. So its details say you got push front, you got push back, and they do have the operator bracket, which is the same as the at operator or at function. You give a position and it'll give you that element efficiently. So I wonder if it has the details. Yeah. Random access is also constant. Putting stuff at the beginning or the end is constant, just like a linked list would be. And if you put something in the middle of the deck, double-ended queue, it takes linear time. So when you're thinking about which of these are the three common ones, which of these three to use, you got to think about those factors. Are you going to be doing, this one doesn't have the big O for some reason. Are you going to be doing a lot of inserts at the front, a lot of inserts on the back? Are you going to be mixing those up? Are you going to do a lot of inserts in the middle? In which case, probably nothing's all that efficient. Are you going to go left to right or want to jump around randomly? So those factors help you decide which of these containers to use. They all otherwise work the same. You got push front, push back, and so forth. And then set is another version of container where it prevents repeats. And usually it's just going to do the right thing. If you say I have a set of integers, it'll know when two integers are equal. If you have a set of your own special kind of class, you might have to tell it how to compare elements in your class. But notice there's no push back, push front because sets don't necessarily have an order. These kind of sets keep their order, but still sets don't really work that way generally. So they call it insert and erase instead of pop. So you insert into a set, which means you do things like, if you include set, you do something like my set.insert, and then if you do it twice, you should see that there's still just one thing. Yes. So prevents duplicates. And then there's also another kind of set. It's called unordered set. And so sets actually do keep in order. It's how they stay efficient. An unordered set, it may not keep the order. And So because it doesn't have an order, allows fast access to elements since it's always the same place. And yeah, so minor differences there. And then the other important thing is called a map. So a map takes two parameters in the template. A map is a key value pair. So you have to say what the key is, like integer or string or something. You have to say what the value is, which they call t. Include map. In the case of map, you would say something like, I'll put it up here, map string int, for example. And then there's a couple ways to add things. So map could do adding by insert. And when you do an insert, there's a whole bunch of varieties of this same function, but you could say insert, where's the version I want? Okay, so I don't really want insert because I have to make a pair object. Yeah, so most likely what you're going to use here is the brackets syntax, because that allows you to set values. This is a lot like the operator brackets that you've defined before. So you're going to do something like this most likely. You can do an insert if you establish a pair, which requires include pair. But if you don't want to make a pair, you can say my map. If this is you're counting words, you could say hello appears 5 times in my map. Goodbye appears 3 times, and so forth. So if you do my map.size, then you get 2 things. And all these have a way to erase an element as well, so you can look that up. And if you want an overview of all the operations that are available, because I mentioned a bunch of stuff, push back, push front, insert, erase, and so forth, there's a nice table down here. It's actually quite a large table because there's a lot of operations and a lot of different kinds of containers, but the ones that you are going to be most interested in would be vector, dec, list, set, map, and possibly unordered set. So they've all got a constructor, of course, and they've got a destructor because they have to deal with their memory. We'll talk about iterators in a second video. So at, or operator bracket bracket, that's effectively the same as random access. That's saying jump to a position, or in the case of a map, jump to a key. They're basically synonyms for each other. So notice vector and dec support that, list does not, and set does not. So these are literally just not defined. There's no reason to use these. It doesn't make sense really for a list or a set. For inserting and vector, you can insert dec. Insert allows you to insert any position. I'll talk about later in a second video how to get to a position. So all of these support insert. They may or may not be very efficient about it. For push front, vectors don't support push front because that's going to be slow. It requires copying everything one position over to make space for that new thing in the front. Even if you've got the space reserved in the vector, it still requires everything get copied over. But decs are designed, they actually have a lot of little arrays, little chunks. So it's pretty efficient to push front because it only really copies a few elements in that chunk. So it does have push front defined. Naturally, a list, a bidirectional list, has push front defined. And then these other guys, set, map, and unordered set, there's no real concept of front, so you don't push front. Likewise for popping, push back, vector does have push back, and a dec does, and a bidirectional list does. Notice the forward list does not have push back, but it does have push front, and the others don't have push back because there's no real position. And then pop back, and I'm looking for the insert, and I guess, okay, so sets have insert and really nothing else. Likewise, maps have insert and really nothing else except the brackets. So anyway, whole variety of functions and combinations of which ones support which things. And Some of them, as we'll see later, have their own definitions for what find does. We'll talk about find in the second video. How to sort. Sometimes they have their own sort functions and so forth. But the main things you're going to see in practice would be pushing and popping front and back, or insert. See erase and operator bracket if that's allowed. And of course you can clear any of them. That erases all the contents. And they should all have a size, actually. Well, curiously, forward list doesn't have a size. I guess it would take too long to compute it. All right, so here's the basic usage. If you want more examples of usage, we have notes here, vectors, and then maps and sets. What's also in those notes is how to walk through these containers. Now, obviously, walking through a vector is trivial because you can just go to position 0, 1, 2, up to size in a for loop. But these don't have positions. So how do we go through them? And what this library, this container library, or STL, what's so valuable about it is most of these containers have some properties that are common among all of them, which means you can define algorithms like sorting and finding and other things like that in a generic way. If you give those a container, as long as the container has certain functions defined, it doesn't matter how the container works, it'll be able to go through that container. So we'll talk about that in the next video.